Hello and welcome to another lesson on trig identities and equations. So we've had the first lesson, which has been a fairly in-depth explanation of the cast diagram, which will make more sense as the chapter progresses, please trust me on that. And today we're going to have a look at what we call exact trig ratios, sine, cos, tan of 0, 30, 45, 60 and 90, which you should have seen at some point at GCSE, so those are going to be recapped. And as well, we're going to have a look at how we can apply those exact trig ratios to example using the cast diagram. And we're going to have a look at some new trigonometric identities, which we can derive from how we define the unit circle. So without further ado, let's have a look at the warm-up questions as usual. Here they are. So questions 1, 2, 3 and 4. Try these on your own. When you're ready to see the solutions to them, press play and let me talk you through the answers so you can see if yours match mine. So without further ado, let's have a look together at how we do question 1. So here's question 1. Consider the 2, 2, true equilateral triangle below. So I've called this triangle ABC, so each side of it's got side 2. So what we're going to do here is derive the exact trig ratio values for 30 and 60 degree angles. And the first thing we're going to do is the first step. So step A, what we're going to do here is split the triangle in half by drawing a perpendicular line from the middle of side BC upwards so it bisects angle A. And then we're going to label the midpoint of BC as point D. So we're just going to draw a line going up from the middle of BC from here all the way up to A, which bisects A. So we need to have something like this. So the blue line is going to be the angle bisector of A, and point D is a new point we've made, which is halfway in between B and C. The second step, step 2, or part B, we need to now label the angles on the newly constructed triangle ABD, so this triangle on the left. You could use ADC if you wanted, I suppose, but let's just go for ABD here. Also, as well, we're going to label the side length BD. So we should have something like this. From B to C was 2, so if D is just halfway from B to C, BD will be 1, and of course DC would also have a side length of 1. Because we defined this as an equilateral triangle, angle B will be 60 degrees, and the angle BAD will be 30 degrees because it was bisected by this line AD. So angle A, which was 60 degrees, has been split in half to make angle BAD, which is 30 degrees. The next step is we're going to use Pythagoras to find the side length AD. So what we're going to do here, which is important, we're going to leave this answer in exact form. So how could we define AD? How could we work this out? So using Pythagoras, the longest side all squared, which is AB, so AB squared is going to be BD squared plus AD squared. Now we can just substitute in what we know. AB, we know. AB is 2, so this means 2 squared equals BD squared. BD is 1, so that's 1 squared plus AD squared. We can now make AD squared the subject and rearrange. So AD squared, there'll be 2 squared minus 1 squared, which is 4 minus 1, which is 3. So therefore, AD is going to have a length of root 3. So then we can label this on the diagram, like so. Now we're nearly there. So this next step is now we've constructed ABD, all its angles and all its sides, we can consider the angles ABD and BAD and the fundamental definitions of the trigonometric functions. We can now write down the values in exact form of sine, cosine and tangent of 30 degrees and of 60 degrees too. So let's just think about these each in turn. So thinking of this 30 degree angle here at BAD, we can consider sine 30. So sine 30 is defined as the opposite side divided by the adjacent. So for sine 30, for this angle here, the opposite side is 1. So sine 30 is going to equal 1. divided by the hypotenuse, which is 2. Remember, sine is always opposite divided by hypotenuse, so it's going to be 1 divided by 2. Still considering this angle of 30, the cosine is always defined as the adjacent divided by the hypotenuse. So the cosine of 30 is going to be the adjacent side, which is AD, which is root 3, divided by the hypotenuse, which is this side AB, which is 2. Now for tangent. The tan function, tangent, is defined as the opposite divided by the adjacent. So for this one here, the opposite is 1 and the adjacent is root 3. So that's going to be 1 divided by root 3. Now we could write this with the denominator rationalised. So if we multiplied both top and bottom of this fraction by root 3, this is the same as saying it's root 3 over 3. So tan 30 is a third of root 3, which is one and the same as 1 over root 3. So now we've dealt with the 30-degree angle, we can now consider the 60-degree angle at B. So first of all, sine 60. So sine 60 is the opposite side, which is root 3, divided by the hypotenuse, which is, again, 2. So sine 60 is just half root 3, or root 3 over 2. Cosine 60 is the adjacent side, which is 1, divided by the hypotenuse, which is 2. So cos 60 is going to be exactly 1/2. And tan 60 is the opposite side divided by the adjacent side. So for this triangle ABD, we can see that tan 60 is root 3 divided by 1, which is obviously just going to be root 3. And so that's question 1 done. We've now found the exact forms of sine, cos and tan of 30 degrees and 60 degrees. So now we can have a look at question 2 and find the exact trig ratios for an angle of 45 degrees. So first of all, we have this triangle here, which is called XYZ. It's a right-angled triangle. Angle X is a right angle. So with 3 steps, we're going to be able to define sine 45, cos 45, and tan 45. So let's think about this now. So first of all, let's label on the diagram the sizes of the angles XYZ, the angle at Y, and the angle at Z, which I've called XZY. So if you view the question carefully, it's an isosceles triangle. So if this one's 90, the other's going to be 90 divided by 2, which is 45 degrees. So both of these here are going to be 45 degrees. The next step is we can now use Pythagoras to find the length of side YZ, and that can be labelled on the diagram and left in exact form. So YZ all squared is going to be the length of this side squared plus the length of the other side squared. 1 squared plus 1 squared is 2. Square root both sides. Therefore, the length of YZ is going to be root 2. So that can be labelled on like this. The next step is just by considering either one of these angles at Y or Z and the fundamental definitions of the trig functions, we can write down now the values of sine 45, cos 45, and tan 45. So first of all, let's just think about sine. So the sine of an angle of 45 is going to be the opposite side to the angle, which is 1, divided by the hypotenuse relative to the triangle. So opposite the angle is 1, divide that by the hypotenuse, which is root 2. So sine 45 is 1 over root 2. That's fine. Or we could rationalise the denominator by multiplying both top and bottom by root 2. If we do that, we'd get root 2 over 2. Now for the cosine. So again, if we just use angle Y, the cosine is the adjacent divided by the hypotenuse. So the cos of 45 is the adjacent, which is 1, divided by the hypotenuse, which again is root 2. So for an angle of 45 degrees, the sine is the same as the cos. It's 1 over root 2. And again, that can be rationalised like before to give us root 2 over 2. Finally, tan tan 45 is the opposite, which is 1, divided by the adjacent, which is 1. 1 divided by 1, tan 45 is exactly 1. Next up, we've got a triangle PQR which I've labelled and shown below twice. So imagine first of all angle alpha. Alpha's this symbol here. So imagine angle alpha in this first triangle approaching but not quite reaching 90 degrees. So as this happens, imagine the effect of a small angle beta. So as this one here, alpha, goes towards 90 degrees, this one above is going to simultaneously be shrinking towards 0, but again, never quite reaching. So if we just imagine this, we can then work out what sine, cos, and what would happen to tan alpha would be as alpha grows and grows towards 90 degrees. And so these other side lengths may vary, but the hypotenuse is fixed at 1. So just imagine a triangle PQR being squished in, so QR is going to be squished closer and closer this way, so this angle here is going to get steeper and steeper. To demonstrate what I mean, I have a little graphic here to just show you the effect as QR moves to the right and alpha approaches 90 degrees. So here's the graphic I'm talking about. So there's angle P. It goes a bit too fast, I'm sorry about that. Then QR is getting squished in. So QR, as you can hopefully see, is going to go closer and closer to P until eventually QR is one and the same as the hypotenuse. And so QR is going to go closer and closer to 1. So sine 90, remember how sine is defined? So this is going to be the opposite side, which is QR, divided by the hypotenuse, which is 1. Now QR, I'll show you again in a second, is going to become closer and closer to 1. So in the limit of alpha actually going towards 90 degrees and becoming it, QR will be 1. If you see here again, QR is going to get closer and closer and in fact become the hypotenuse. So QR over 1 will become the same as 1 over 1, which of course is 1. So the sine of 90 is 1. In a similar way, the cosine of 90, cosine is the adjacent side, which is PR, divided by the hypotenuse, which is 1. And again, just showing you the image, have a look at what happens to PR as alpha gets closer and closer to 90. PR is the bottom side. We can see here it shrinks down to 0. And so in the limit of alpha becoming 90, PR becomes 0. It vanishes to 0 as the angle becomes 90. So PR becomes 0, hypotenuse is fixed at 1, by how I created the diagram. 0 divided by 1 is 0. And so sine 90 is 1, cos 90 is 0. What happens to tan alpha though, as alpha itself approaches 90 degrees? Well, tan is always going to be the opposite side, which is QR, divided by the adjacent, which is PR. And so as alpha goes towards 90 degrees, the side QR goes towards 1. But the main thing to notice is this bottom side, PR, I'll show you again, PR goes smaller and smaller towards being infinitesimally small. PR approaches 0. So in other words, as alpha approaches 90, QR over PR goes towards 1 divided by a tiny, tiny, tiny value. As it gets smaller, it goes towards infinity. You can't actually do 1 divided by 0, it's undefined. So tan 90 is undefined, but we can say that as alpha gets closer and closer to 90, without actually strictly ever becoming 90, that the tan of alpha will tend towards infinity. So that's the idea of a limit. It's a concept where we can get closer and closer to some value without ever quite actually being it. Now let's think about beta, this angle here. And so as beta gets smaller towards 0, we can think about sin, cos and tan. So again, we can use this image, but instead of focusing on alpha, we can focus on the top angle at Q. So again, here's the image once more. So as angle Q gets smaller, we can see the effect on QR relative to PQ. So as beta gets smaller towards 0, QR becomes QP. So sin theta is the opposite side, which is PR, divided by the hypotenuse, which is PQ. Now PR, this side gets smaller and smaller as it gets towards 0. QR looks to be going in like this. So PR goes to 0, and PQ, this one here is 1. 0 divided by 1 is 0. So sine of 0 is 0. Cos 0, well, cos is the adjacent side, which is going to be QR, again divided by the hypotenuse, which is PQ. Now as this angle gets smaller, you should have seen that QR becomes in effect the same as the hypotenuse. And so the hypotenuse PQ is 1, and QR becomes closer and closer to this, and if cos of beta were 0, it would actually be the same. Just show you the diagram again. QR gets squished closer and closer towards P, and eventually this side gets merged into the same side QR. So QR is 1 and the same as the hypotenuse. So QR over PQ is 1 divided by 1, which is 1. Finally, tan is the opposite, which is PR, divided by the adjacent, which is QR. So PR goes towards 0. QR, as beta goes towards 0, QR becomes the hypotenuse, which is 1. But again, 0 divided by 1 is just 0. So for 0 degrees, sine 0 is 0, cosine 0 is 1, and tan 0 is 0. And that's all the warm-up questions completed. So now we can have a look at the main lesson apart from the warm-up itself. So let's have a look now at thinking about finding exact values of trig ratios. So question 1, think about finding the exact value of sine 120. Okay, so finding trig values or solving trig equations, I would always suggest at this stage to get used to this CAST diagram. So here it is, CASC. Sorry, CAST, can't even read, that's not very good. So first of all, for a CAST diagram, always just draw on an X, centered on the origin. So something like this. Then remember how we measure angles using the CAST diagram. We always measure clockwise from the x-axis if it's a negative angle, but if it's a positive angle, we measure anti-clockwise from the x-axis. So 120 is positive, so what we do is we go around until we get to 120. So here would be 90 degrees. 120 is definitely in between 90 and 180, so it's going to be somewhere in the S quadrant. Okay, so sine 120 is going to be here somewhere. So next up, what we need to do is think about the acute angle in between these lines and the x-axis. And so if this is 120, this is going to be 60, this is 60, they'll all be 60. Okay, so sine 120 is going to relate to sine 60, because if you remember from last lesson, we only need to consider the sine, cosine or tangent of the angle made in between the x-axis and these lines here, which is 60. So sine 120 is either going to be positive sine 60 or negative sine 60. It's just a question of if we put a minus sign here or not. Now, this is where the CAST diagram comes in. So because sine 120 degrees means we're in this quadrant here. So that's 120. And this point is clearly in the S quadrant. And in the S quadrant, S for sin, any sin ratio is positive if it lies in this quadrant. And so sin 120 is positive, so therefore sin 120 is going to be sine 60, which is positive. Remember, any acute angle, sin, cos, tan, for all positive in this quadrant. So therefore, sine 120 is the same as sine 60. But what was sine 60? Again, without using a calculator if you can. So here's a little crib sheet for you. So sine theta, when theta is 60, that's going to be root 3 over 2. So in other words, sine of 120 is going to be root 3 over 2. Double check on a calculator, if you really must. Sine 120 equals root 3 over 2, which is what you'd expect. So we can use these cast diagrams to help us in these situations. Another example, find the exact value of tan of minus 225. So again, let's get the cast diagram ready. Here it is. This time, as you can see, this angle's negative. With a cast diagram, we measure negative angles clockwise from the positive x-axis. So we're going to start here and go this way round. So minus 225. So just sketching it on. That's minus 90. Minus 180 plus another 45. It's going to be somewhere here. So again, draw an X on, like so. Doesn't need to be done accurately, as long as it's in the right quadrant, nothing else really matters. Oops a daisy. There we go. And so an angle of minus 225 is this angle here, and we've ended up again in the S quadrant. And again, we need to think about the acute angle made in between the x-axis and these lines of the x. So minus 225. So this is essentially an angle size 180 plus an extra 45. And so this angle here must be 45. Therefore, all of these acute angles made with the x-axis are all going to be 45 degrees. And again, we've landed up in the S quadrant. And that tells us that tan of minus 225 will link in some way to the tan of 45 degrees, because this angle made with the this acute angle made with the x-axis is 45. The only question now is tan minus 225 going to be positive tan 45 or negative tan 45? And again, this is where the cast diagram comes in and helps us. And so which trig functions are positive in the S quadrant, which is where we are? S stands for sin or sine, so only the sine function is positive here. Cosine and tangent are negative, therefore we say this is minus tan 45. Tan 45, because 45 is an acute angle, tan 45 itself is positive, so we just put minus tan 45 to make this thing negative like it needs to be. But what was tan 45? Again, you should try and remember these, but if not, here they are. 45 degrees, tan 45 is 1. So in other words, tan minus 225 equals minus tan 45, which is going to be minus 1. And again, at this stage, do you now feel free to use your calculator to double check this. The point of this activity, though, isn't just to look at this and use your calculator without thinking. The point is use your calculator to check, but see if you can use this cast diagram to understand why values are what they are. So tan minus 225 is indeed negative 1. The first part of the main lesson is arriving at some very crucial trigonometric identities. And we're going to do this by considering from less Lassen the unit circle in the xy plane. So here it is. This is a circle with radius 1 fixed on the origin. So we need to recall from last lesson a few things. First of all, let's just define any point here as being p, which is a function of x and y, and this angle here made with a positive x-axis going towards this radius as theta, measured clockwise, sorry, anti-clockwise I mean to say, from the positive x-axis. So this is going anti-clockwise. I beg your pardon. So from last lesson, for any point p, xy, on a unit circle such that OP makes an angle theta with a positive x-axis, we said that cosθ, which is x, is always going to be the x-coordinate of this point. Sinθ, which is y, is defined as the y-coordinate of p, and tanθ, which is the opposite divided by the adjacent, which is y divided by x, that's the gradient of OP. So now we just need to add on a few more things. Knowing that it's a unit circle, we need to include here 1 for the radius. Sinθ is the y-coordinate, so the height here is y, sinθ, and the distance along the x-axis is x, which is cosθ from this part here from last lesson. So the first thing we can do is think about Pythagoras. So applying Pythagoras to this triangle here, and labelling on a few important things. We've got here that the y-coordinate, the height, if you like, that's sinθ. This is cosθ. And this is a unit radius, which is 1, and it's a right-angled triangle. So applying Pythagoras to this, we can derive an important identity. So the hypotenuse squared, 1 squared, equals the other two sides squared and added together. So that's going to be cosθ all squared plus sinθ all squared. Now in terms of squaring or raising trig functions to any power, there's a way of doing this so that this squared doesn't get confused with the angle in question. What we do is we put the squared next to the trig function. So 1 squared we just say is 1, but we rewrite cosθ all squared and sinθ all squared as the squared next to the function, like so. So this means sinθ all squared. So sinθ squared, sin squared theta, plus cos squared theta, identity, so always equals 1 squared, which is 1. And so that's one important identity. We also have here that tan theta is y divided by x, but y is sin theta. So tan theta must always equal, hence the identity symbol, y, which is sin theta, divided by x, which is cosine theta. And so these are two absolutely crucial trig identities which you'll be seeing time and time again in your course of A-level. So these absolutely need to be committed to memory. So what I'd like to do now is just to have a look at these in a bit more depth and show you how they are useful by means of a few worked examples involving these trig identities. So first of all, we've got 3 parts to this where we need to simplify each of these identities. So first of all, let's start with part A, which is sine squared of 3 theta plus cos squared of 3 theta. So the identity from before was sine squared plus cos squared is always equal to 1. Now theta can be whatever it needs to be. Theta could be 30 degrees, could be 90 degrees, and it could also be an expression in itself. So sine squared of something plus cos squared of the same something equals 1. So this here is going to equal 1 as well. So what I'd suggest you might want to do is make a little substitution to make it a bit more obvious to yourself. So let 3θ equal big X. But it means it becomes more obvious. And sin squared 3θ plus cos squared 3θ is sin squared big X plus cos squared big X, which has to equal 1. Sin squared θ plus cos squared θ, that's the same thing as sin squared x plus cos squared big X. This has to equal 1. Because we've got here sin squared of something plus cos squared of the same something. That will always equal 1. Here, part B looks a bit more complicated, but here what we need to do is remember this expression here. So we're going to apply the same idea to help us solve part B. So 5 minus 5 sin squared θ. We should now notice that this will now easily factorise. So 5 minus 5 sin squared θ rather, we can factorise that 5 from here. So you've got 5 brackets 1 minus sin squared θ. Now I did say from before that this identity will help us for part B, so I'm just going to actually give myself a bit more space here. And if I bring this down, if I rearrange what's in this box here in terms of 1 minus sin squared θ, I could just subtract sin squared θ from both sides and arrive at cos squared θ must equal 1 minus sin squared θ. Just by rearranging the identity that sin squared plus cos squared is 1. So this helps us because we can now replace 1 minus sin squared θ with cos squared θ. Okay, so next we can say this is 5 lots of cos squared θ. So we can now move on to think about part C, where we have sin squared 2θ all over 1 minus sin squared of 2θ. Now for part C, we can actually use this identity here, cos squared θ equals 1 minus sin squared 2θ. So replacing θ with 2θ, we can hopefully see that cos squared of 2θ is the same as 1 minus sin squared 2θ. So this helps us because we can now replace the denominator with cos squared 2θ. And so sin squared 2θ all over 1 minus sin squared of 2θ. That's the same as sin squared 2θ all over cos squared 2θ. Keep trying to write θ rather than 2θ for some strange reason. Over cos squared 2θ. Now sin squared over cos squared, because sin over cos is tan, sin squared over cos squared is tan squared. And so this is actually the same and equivalent to tan squared of 2θ. And so that brings question 1 of these worked examples to an end. We can now have a look at question 2. So question 2, we have an identity to prove. Now, the best way, in my mind, of proving identities is to start with one side of the identity and manipulate it so it matches the right-hand side. And so if we have a look at just the left-hand side here, what we can do is aim to get it to be 1 minus tan squared θ. So cos to the power 4 θ minus sin θ to the power 4 all over cos squared of theta. You can see here from the top, this is an even power. So with a bit of thinking about it, you might hopefully spot that the top is actually a difference of two squares. So the top can be written as cos squared theta plus sin squared theta. Then cos squared theta minus sin squared theta. All over cos squared theta. Now what we saw from earlier is that cos squared theta plus sin squared theta is always going to be the same as 1. Okay, so the first bracket here, that's actually just going to be equal to 1, which makes it much simpler indeed. So that's just a case of dividing through the numerator by the denominator, which is cos squared. So we have cos squared theta divided by cos squared theta. Just splitting this into two separate fractions, minus sin squared theta, again over cos squared theta. Cos squared over cos squared, anything divided by itself is obviously 1, and then sin squared divided by cos squared equals tan squared theta. So we've arrived at what we wanted to arrive at. We've taken the left-hand side here and changed it to equal the right-hand side. So we started with the left, did difference of two squares, manipulated it, and eventually ended up with the right-hand side. So we've proven that the left equals the right. So therefore, we can just conclude by saying cos to the power 4 theta minus sin to the power 4 theta all over cos squared of theta, therefore is 1 and the same as 1 minus tan squared theta. I've done my old trick of never leaving myself enough space, just about squeeze that on. So now we've proved question 2. For question 3, A and B, we can make use of the cast diagram again. I'll show you how here. So we've told for 3A that given cos theta is minus 3/5 and that theta is reflex, find the value of sin theta. So first of all, let's just get this diagram up and ready. So here's a cast diagram. We're told that cos theta is negative. It's got a negative minus 0.6 value. So we know for definite it's going to have to be in the T quadrant or the S quadrant, because in the S quadrant only sin is positive, so cos is negative, and in the T quadrant only tan is positive, therefore again cos will be negative, which it needs to be here. So it's going to be one of these two quadrants, but we are told that theta is reflex. Reflex means it's more than 180 degrees. So in terms of our diagram, I'll just add on an X shape here. We know, because it has to be more than 180, we're looking for theta in this region down below. So measuring theta anti-clockwise from the positive x-axis, that's 90, 180, more than 180 it's reflex. So theta is this angle here. We now need to remind ourselves of the identity that cos squared plus sin squared equals 1. So therefore, sin squared theta is going to be 1 minus cos squared theta, just by rearranging this. If we then take square roots of both sides, we can see that sin theta, therefore, must be either positive or negative the square root of 1 minus cos squared theta. So cos²θ, well, we're told that cos θ is minus 3/5, so plus or minus 1 minus 3/5 all squared. So you can try this in your calculator exactly as it appears. Obviously, if you're doing minus 3/5 all squared, that'll come out to be positive. It's going to be 1 minus 9/25. So again, you can just type it in as it looks if you want to avoid any confusion or to work anything out that you don't need to. 4/5. So sinθ must be plus or minus 4/5. Just a case of which one it is, either plus or minus. Okay. So bear in mind, we were told that cosθ is negative and reflex. So it's in this region here, it's in the T quadrant of the cast diagram. Now, because θ is in the T quadrant, that also tells us the value of the sine function. Only t is going to be positive here. Therefore, cos and sine are going to be negative. So from this, we can say that therefore, sinθ must actually be the minus option. So sinθ has to be minus 4/5. The reason being just simply because θ is more than 180 but less than 270. Or you can say because it's in the T quadrant. So we can say because it's in this section here, then θ has to be between 180 and 270. In fact, to just be perfectly accurate, I'll leave the inequality like this, so there's no ambiguity. Now, 3b is very similar, in fact. So for 3b, we're given that sine alpha is 2/5 and that alpha is obtuse. We need to find the value of cos alpha. So again, let's have our cast diagram ready to hand. Θ is obtuse, so that means that θ is more than 90, but no more than 180. If it were more than 180, it'd be reflex, which it isn't. So just using our cast diagram here, put the x on. Because θ is obtuse in this case, sorry, not θ, alpha rather, is obtuse, it's going to be in this S quadrant here. That's 90 degrees. He is between 90 and 180. So this is alpha. So we're wanting to find the value of cos alpha. Again, though, we need to use this trigonometric identity to help us. So cos² alpha plus sin² alpha equals 1. So that can be rearranged in terms of cos² alpha. So cos² alpha is 1 minus sin² alpha. And so cos alpha is going to be plus or minus the square root of 1 minus sin² alpha. Sin alpha is 2/5, so it's 1 minus 2/5 all squared. We can then work out if it's going to be plus or minus by using the cast diagram. But first of all, let's just find the value of this. So minus 2/5 all squared from 1. So that matches. So it's going to be plus or minus root 21 over 5, either plus or minus. So now let's consider if we want this to be positive or negative. So we know that the angle we've got, alpha, is in this quadrant here. It's in the sine quadrant. In other words, sine is positive here, and it's obtuse. So in this quadrant where alpha is, only sine is positive. S means only sine. So cosine and tangent are both negative. So because of that, the cosine must have a negative value. So therefore we can just say that cos of alpha must therefore be negative root 21 over 5. Again, if you needed a reason, not that the question's asking for the reason, it's because of where alpha is situated in this second quadrant. So alpha is between 90 and 180. Finally, question 4. So given that P is defined as 3 cos theta and Q is defined as 2 sin theta, we need to show that 4P squared plus 9Q squared equals 36. So let's just take the left-hand side and see if we can change it and manipulate it to be 36. So 4 lots of P squared means 4 lots of 3 cos theta all squared, and 9Q squared means 9 lots of 2 sin theta all squared. All I've done here is just use the fact that P is 3 cos theta, so P is this, and that Q is 2 sin theta. So I've just taken Q here and replaced it with what Q is in terms of sin theta. So 3 cos theta all squared, we do 3 squared first, which is 9. Then cos theta all squared, we write as cos squared theta. Then plus 9 lots of 2 sin theta all squared. Well, 2 squared is 4, and sin theta all squared we can write as sin squared theta. So we can now multiply these out. So 4 times 9 cos squared theta is 36 cos squared theta. Then 9 times 4 sin squared theta is 36 sin squared theta. Now each of these have a common factor of 36, so we can factorise out 36. So it's 36 lots of cos squared theta plus sin squared theta. But now, if we remember back to the earlier part of the lesson, we need to remember that sin squared theta plus cos squared theta, this is a crucial trig identity, that's always going to be equal to 1. So in other words, all of this thing here in the brackets is just going to be exactly equal to 1. So we've proven it, because 36 lots of cos squared theta plus sin squared theta means 36 lots of 1, which is obviously just 36. So therefore, 4p squared plus 9q squared is indeed 36. And we're done and dusted. So now it's over to you lot. So, ladies and gents, if you could go to page 209, exercise 10b, try questions 1a through to j, and once you've tried those and done those, page 211 to 212 of exercise 10c, questions 1 through to 3, question 5, question 10, then the examination type questions 11 and 12. So try those, and do be checking your answers using the answers at the back of the book, and if, as ever, if you're unsure at any point, do ask me or a peer if I'm not to hand. Come and see me, or ask me on an email if you're still struggling, and I'll do my best to help you out. So try those, and you'll see me again very shortly indeed. So thanks for listening once again. Remember to subscribe if you could do, please, and keep working hard. Thanks for now, and goodbye.